So hi everybody and welcome to this sixth video on in phase equilibrium series. So in this video we'll be going through the phase diagram of a single component system, which is carbon dioxide. The phase diagram is as follows for the carbon dioxide. So we have pressure in y-axis and it is represented in atmospheric pressures, okay, and we have temperature in x-axis, which is represented in Kelvin scale, and the diagram is of this nature. Okay. So here is your solid phase, there is a liquid phase, and there is a vapor phase. This is your triple point. So let us see the salient features of both of these of this diagram. The first thing to notice is that there is a positive slope for the solid liquid phase boundary. So I'll just write here so you can just look at this diagram. First point is the positive slope, the solid liquid phase boundary. So the direction of this line is characteristic of most substances. That means the positive slope is characteristic of most substances. So what this slope indicates is that the melting temperature of the solid CO2 increases as pressure increases. As simple as that. The second thing to notice is, I'm not, of course, not given you the values, but if I put values, okay, so this corresponds to at about 5.11 atmospheric pressure, okay, so which means at 1 atmospheric pressure, no matter what your temperature is, you are not going to get a liquid carbon dioxide, okay, and at about 25 degrees Celsius, which happens to be your room temperature, the corresponding, of course, this is not to scale, this is a very, so this pressure, corresponding pressure happens to be 67 atmospheric pressure. So just compare the values here. So the triple point exists, the triple point exists well above 1 atmospheric pressure, which means the liquid cannot exist at normal atmospheric pressure no matter what the temperature is. As a result, the solid, when left in open, sublimes to gas when left in open. That is why you have the name dry ice for carbon dioxide. So I'll just write it down. See here, no matter whatever the temperature, you are not going to get liquid carbon dioxide. Solid carbon dioxide will sublime into vapor phase if you just keep it open at a room temp at atmospheric pressures. So that is why the name dry ice is given. So so this implies that liquid carbon dioxide cannot exist at normal atmospheric pressures. Whatever the no matter what the temperature is. So as a result, the solid CO2 sublimes to vapor directly without going through the liquid phase to vapor phase directly when left in open. That is why the name dry ice is given for carbon dioxide. So given this, let us also understand how does your uh, carbon dioxide fire extinguishers work. So what is there in them that it can extinguish a fire. So now you already seen the phase diagram. Where is it? It must be. So this is your phase diagram. Now, if you want to obtain a liquid, it is necessary to exert a higher pressure of of at least up to 5.11 atmospheric pressure. So that's a higher pressure compared to 1 atmosphere that we have at room pressure. Now, cylinders, that is fire extinguishers containing carbon dioxide, generally contain liquid or compressed carbon dioxide gas. So at 25 degree Celsius, they need to have a vapor pressure of at least 67. If this is your 25 degree Celsius, see they need to have at least vapor pressure of 67. So pressure should be maintained at 67. Atmosphere if both gas and liquid CO2 are to be in equilibrium. Now, when the gas is released through a tap, which acts as a throttle, when gas is released, now what happens is the gas is now introduced to a lower pressure of 1 atmosphere. So this is where your Joule-Thomson effect kicks in. So Joule-Thomson coefficient mu Jt is given by delta T by delta P, which is like T final minus T initial and P final minus P initial. Now let us put these values. Now if it is brought down from 67, no, your final is 1 atmospheric pressure and your initial pressure is 67 atmosphere. Now your initial temperature is 25 degree Celsius. Now this mu Jt for carbon dioxide is a positive value. So which means your T final should also be lower than this, only then you will get a positive value, right? So if this is minus 66, this also has to be minus negative value, right? So what happens? Temperature, simple, adiabatic expansion. When adiabatic expansion occurs, temperature decreases. The whole thing about Joule-Thomson effect is it is a liquefaction of gases. So which means the temperature decreases, and because the temperature decreases, the gases liquefy or solidify. They condense. So the gas cools by the Joule-Thomson effect. So it, and pressure is already reduced. So what happens is it condenses. As a result, it condenses into a finely divided snow like solid, and this covers the fire and does not allow the fire to get exposed to oxygen, which is necessary. So that is how this forms the basis of carbon dioxide. Carbon dioxide fire extinguishers. Okay. Another important physical interpretation is that carbon dioxide gas cannot be liquefied except by applying high pressure, reflects the weak reflects the weakness of the intermolecular forces between the non-polar carbon dioxide. See, the carbon dioxide is non-polar, right? Neither this, there is no net dipole. It's a non-polar. Therefore, how will it get attracted to each molecule, another molecule of itself? So it's very, there is a weakness in the intermolecular forces. That is why it cannot be compressed as easily except by applying very high pressure. So that was about your phase diagram of a single component carbon dioxide system. Thank you. Next, up next will be water system.